So we're down to Windows overflows. So there's some slides and then some demos. Let me get this. All right, that looks pretty good. Okay, so all right, we're going to talk more about how Windows software works, and that's the main thing. We talked about both this and the malware analysis course. Understanding how operating systems work is a lot of it. So there is a thing called the thread environment block and the process environment block. Remember, we talked about this before. If you go into Task Manager, in fact, I should be able to do it. Yeah, here's my Windows machine that's running. So if I go into Task Manager, which should be down here again, yeah, Microsoft put it back where it belongs. They tried removing it, like they like to hide everything, and everybody complained, they put it back. So here's Task Manager, and there you can see the processes that are running, and then the number of threads each process has. So there's a lot of processes running in background, and Firefox has about a dozen processes, and each one of them has a certain number of threads, like 88 threads, 15 threads, and those are little pieces of the running process that can proceed independently. So each one of them has a thread environment block, which stores the information about the thread, and all right, and like I say, this is technically undocumented, but in fact, people have learned about it so much that it's effectively part of the API now. So this can be used to get a lot of information. You get the last error, the import address table, startup arguments, and so on. And that's because each thread gets a few cycles of processor, and then it goes to the next thread and the next thread, and that's called a context switch. So it has to store the environment, like all the registers, and then it has to recover it when it goes to the next thread. So there's overhead involved in a context switch, from moving from one thread to another thread, and your computer is strobing through all these threads very rapidly. They each get an instant of time, then the next thread gets an instant of time. So some of the time is overhead, saving the current state of this thread and loading the remembered state of the next thread. So here's the thread environment block with stuff like this: the stack base, the stack limits, the structured exception handling frame pointer, the sort of things you need. Now there are segment registers in the processor left over from very early operating systems and not used much, but FS in fact is used on Windows 32-bit to point to the thread environment block, but I don't know if anybody's using 32-bit Windows anymore. Pretty much they aren't. So the process environment block is another data structure for the process as a whole. Now, the processes do not directly get any CPU time. It's the threads that do. The process is just a container for all the threads. That's how it works. Anyway, so this, again, is mostly intended for only internal OS use and only partly documented. But here's some of it that's been figured out, like whether it's being debugged, a pointer to process environment block data structure, the process parameters, the session ID, and so on. Information. People have reverse engineered Windows enough to somewhat map out what's going on in the process environment block. Yeah.
From the task manager, I'm able to at least locate the processes as well, right?
Yeah, that's right. You can see the processes and you can terminate them. And if you load Process Explorer, you can even see the threads. And you can even see somewhat what's going on with the individual threads. And for debugging a program you're writing, that could be useful. But it's not normally a normal user doesn't go down any deeper than a level of process. You kill a process that's hung, that sort of thing. So, all right, so in stack buffer flow overflows, we talked about a lot, and this is the classic one. You have a string variable. You're able to override the limit of it, so you add a bunch of data here. You add nop, 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 and then an egg is your exploit. Then you hit the return value, and when it tries to return from this routine, it goes to the EIP you put here, and you change that to point back here to the nop sled. This is what we've been doing in the projects. This is the classic aleph null type buffer overflow that was explained in an issue of FRAC about 30 years ago. This was the major technique used for all the Windows malware up through Windows XP. And so another way to do it is to overwrite the structured exception handler and then trigger an exception. So instead of hitting a return value stored on the stack, you hit the exception handler and then execute an exception, and it again gives you an ability to change the EIP to point to some code you've injected. So if the structured exception handler, you would again find something like an overflow of a string, and you'd overwrite the exception registration data. And then you trigger an exception, and again you control this address, so you point to your nop and your egg. and you run whatever exploit you've done. All right. So to address several strong defenses ended this technique largely for Windows XP and pretty much ended it for Vista for a couple of years until the attackers learned ways to get around it. Address-based layout randomization is the simplest one. In the old days, you would just load Windows at the lowest memory, then the next product, the next memory, next memory. Each application would just load at the next block of available memory, so you could pretty much figure out where it's going to be in the running server. But with address-based layout randomization, it randomizes each one of these separately. Every time you restart a process, it'll randomly relocate this, so you have no idea where any of these absolute addresses are. So the way to avoid it, then, is to find a jump ESP that doesn't move. So find some module that does not have ASLR turned on, so it doesn't move, and then find a jump ESP command in there, which are very common. And now you can go there to that jump ESP, bounce off it, and then you control the AP, you can go back to where this belongs. Because the stack typically points to somewhere in the data you're feeding in. So that's what this is a trampoline, they call it, attack, where you bounce off one command and come back.
The book,
Yeah.
do I understand correctly that the book says you can use either the jump ESP or,
Yeah.
or also a call function?
Sure. Call would do it. You can also have a pop before that. Any command that takes you back to a location. Yeah. And if you find something else like a jump EBP or something, that might be all right. Usually jump ESP is what you'll find.
Your goal is that you want to get back into the
That's right. Yeah. Yeah. You just want to find something that will point to the data even though you don't know where it is. All right, that's one technique. By the way, now the older Windows actually left the address of the structured handler in EBX, so you could easily find it to override it. Newer versions clear all the registers, but the SEH address is at ESP+8. So another thing to do is find pop return, which is another thing you'll see often, and then put it in the structured exception handler, and it'll again do the same kind of thing. So these are ways to do it. Yeah. Yeah.
I don't remember the difference between null and null op in terms of this work.
I don't know. Oh, not. Oh, okay. Null is just a 0. And the point of null is a null pointer will cause a crash. Should I resolve a null? Now, nop is just a command that does nothing.
Yeah.
It's an instruction. Yeah.
I don't want null in the code that I'm injecting.
That's right. You don't want null because it terminates strings.
Okay.
Yeah. And typically that will end your exploit, although sometimes you can get away with it. But usually nulls break the string. Yeah, that's right. Good. Very good to get those separate. All right. So anyway, then there's exception handlers. This is what Windows uses. So if you, each procedure has its own stack frame, and it has at least one frame-based exception handler. Every thread has an exception handler, which is a list of addresses for code to use when there's an exception. And so it looks like this exception, each thread environment block has an address, the exception registration structure at FS0, and so it'll try to do the exception handler, and if this does not handle it, it'll go to the next one and the next one, and if all of them fail to handle the exception, it will go to the operating system, which will then pop up a generic box saying this process has crashed. That's what happens. And this, like I say, is why professional coders spend most of their time handling exceptions, because you never want to have your program just crash. If anything bad happens, you want to handle it gracefully inside the app if you're a professional coder. All right, so here's the kind of code you'll have. Here's your exception handler. It goes in here, and then in here, this one just prints out a message, but the real one would read the number identifying the exception and then take some kind of appropriate action, like fix the problem or pop up a useful box to the user telling them what to do, that sort of thing. So in immunity, you can see the exception handler, and here you see it's just pointing to some library routines in NTDIL. This is Notepad. Notepad just points to 3 different library routines, same one twice for some reason. That's the exception handlers you'll see there. And so if you follow the address in the stack, you'll see here's the pointer to the SEH record and pointer to the next SEH record and so on. So they're just sitting there. And so if you overflow the stack to hit the return address, you'll also overwrite other variables by accident. In particular, you also hit the stored EBP, so you often cause exceptions, and you've seen this in the buffer overflows we've done. We could redirect execution, run some function, but then it would usually crash after that because we weren't careful enough. Now, if you carefully overwrite the EBP with the correct value, you can even do a buffer overflow, run something extra, and then resume without crashing it. We've just been sloppy in our attacks. Anyway, All right, to gain control of exception handling, you can use EBX. On later versions, they're all zeroed to make exploitation more difficult. But in old Windows processes, EBX would point to the exception registration structure, so you'd overwrite it with jump EBX, and EBX points to a location where you can put your code here. You can use a jump EBX as part of a two-step trampoline, and we'll do this in the project, this sort of thing. There's a version of it that also works in modern Windows on certain kinds of software. So if your stack at a crash is like this, notice the third value on the stack points to the exception handler, 17BFFC4.
Second.
FC 40. Anyway, this third value here points to the exception registration structure, and so if you do pop return, you will enter the exception handler. And here we were able to overwrite the exception handler and put letters in there so we could put in an address. And that's the idea. All right. There are various protections that have been added in Windows 2003 Server. They've tried to make sure the handlers are valid. So if handlers on the stack, that's considered invalid. And there are certain handlers they decided to call invalid for Windows 2003 Server, but there are ways to exploit it. You can abuse an existing handler or put your code in a place that will pass this test. And in Server 2008, a bunch more defenses were added. A normal SEH attack looks like this. An exception will cause it to be called as an exception handler. And then you end up going here and going through these things. That's a normal SEH attack. Microsoft added Safe SEH in Visual Studio, so it creates a whitelist of exception handler addresses. So if you recompile old code with the new defense, then it will not let you enter exception handlers anywhere except at the official addresses. You can't enter at that's where you're finding a pop return. And SE hop is another way, verifies the exception handler is intact before using it. It hops through all the exception handlers to make sure they're all pointing to the next one validly. So in case somebody has broken the chain. This, by the way, is true. The Cisco has a defense called check heaps that does the same thing. It walks the heap. It goes through every heap data section, go up to the next one, and hops back to make sure it's not broken. It's so this is one defense. And so that will see if anyone has broken it. So SE hop will add an extra registration record at the end, walk to the end, and make sure it gets there. And that'll detect corruption of the pointers in the chain of pointers. So that's SE hop, hopping through them. All right, and so SE hop is enabled by default and also disabled by default on the client versions of Windows 7 and 10, probably 11, because the client versions are expected to run old software without crashing. Server versions are not really. So there are a lot more defenses turned on by default in server versions of Windows than in clients, because home users often run old games and stuff. You can control it here. Disable exception chain validation is deep in the registry. You can turn this on or off, whether you want to have this feature enforced with disable exception chain validation. All right, and if you do have exception chain validation and you attack the SEH, then you'll get this message, debug program is unable to process the exception. That's what happens when you get busted by SE hop. And it'll happen to us in the projects. So let's take a look at the Kahoots, which are here. This is lecture 9.1, or wait, this is 8A, here we are. Yeah, good. All right.
So basically, if the pointer was on the stack, was automatically considered invalid.
Yes, it won't let you put the handler on the stack.
The pointer of the end.
Yeah.
Yes. But then they introduced a list of registers to sit in.
Yeah, and you can only go to the official point. Yeah.
And so, and what's the additional element of the other versions, the most recent version?
The most recent one there, you also cannot break the chain. So you can't have a corrupt pointer. That's right, just more and more tests. And it's very similar heap overflow tests in modern versions of Windows 2 to just see if the heap structure has been corrupted.
So you look for continuity, something that
Yeah.
tells you that it's
Yeah, and therefore, yeah.
Similar to the counter. When do we use the counter? We use
It's
the
like-
counter to see if the numbers are in the right progressions.
Yeah, that's true, but it's like the canary on the stack. Canary on the stack is a similar defense. Yeah, good. Yeah, sure, that's good. All right, let's give it a shot. All right, switch defense is enabled in servers, but not clients. That's SE hop. All right, you can turn it on in the client and you can turn it off in the server, but by default, it's set up this way. All right, which defense cannot protect legacy code? Yeah, that's safe SEH. You have to recompile code with this switch to enforce these entry points. All right. All right, which method only works on Windows machines before XP Service Pack 1? Jump EBX. They left an important variable in EBX when returning from any subroutine. They fixed it with Service Pack 1. All right, which method finds the SEH in modern Windows versions with ASLR enabled? That's pop return. It's still on the stack, and you can find it there. All right, which register points to the thread environment block? FS, that points to it. SEH is not a register and PEB is not a register. FS and GS are.